pressure and winds are invisible elements of weather which influence other weather elements in a significant way. Air pressure is closely tied to other elements of weather in a cause and effect relationship. Variations in the air pressure from place to place are responsible for the movement of winds which serve as a means of transporting heat and moisture from one region to another. Ordinarily, we fail to perceive the small changes in pressure, but they are very important in bringing about changes in our day-to-day weather. Besides, air pressure is all the more important weather forecasting. Regional variations in pressure are produced by temperature, but there are several prevailing wind systems which are caused by the dynamic factor of the rotation of the earth. According to Trevarta, the atmospheric pressure and winds are not so important as weather elements. Rather, they become crucial to all the life forms on the earth as of temperature and precipitation. As climatic controls, pressure and winds play the most dominant role through their effects upon temperature and precipitation. After this lesson, you will be able to understand air pressure and variations in pressure and weather. You will be able to understand the basic atmospheric patterns. Like any other material object, the air also has weight. The pressure of air at a given place is defined as a force exerted in all directions in consequence of the weight of all the air above it. Thus, the mass of a column of air above a given point determines the atmospheric pressure at that point. Air is a mixture of several gases. In order to clearly understand the concept of air pressure, the behavior of gases and the principle that governs this behavior must be understood. Gas molecules are in a constant state of collision and move about freely. If a gas is kept in a closed vessel, this motion is restricted by the walls of the container. The gas molecules exert an outward push because they continuously dash against the walls of the container. Similarly, our atmosphere may be deemed to be a closed container bounded by the Earth's land to sea surface far from below and from above by the force of gravity that does not allow it to escape to the outer space. Air pressure, therefore, is defined as the force exerted against a surface by continuous collision of the gas molecules. The amount of pressure exerted by air at a particular point is determined by two factors, namely temperature and density. Since air pressure is proportional to density as well as temperature, it follows that a change in either temperature or density will cause a corresponding change in the pressure. The following equation, called the gas law, describes the relationship between pressure, temperature and density. Pressure is equivalent to density into temperature into the constant. So, according to the gas law, an increase in either density or temperature will cause an increase in the pressure provided the other variables, density or temperature, remain constant. The atmosphere exerts a pressure of 1034 grams per square centimeter, 14.11 libidons per square inch at sea level. This amount of pressure is exerted by the atmosphere at sea level on all animals, plants, rocks, etc. The reason that man does not feel the weight of atmosphere falling on his shoulders is because the air inside him exerts an equal amount of outward pressure balancing the inward pressure of the atmosphere. Since air pressure decreases with increasing altitude, at a certain height, this balance between outward pressure exerted by the air inside the human body and inward pressure exerted by the atmosphere outside is disturbed, resulting in marked physiological disturbances such as nosebleed, ear bleed, etc. The mountaineers have to face a lot of difficulty because of the much reduced atmospheric pressure at greater heights. This is so because the higher we go, the thinner the atmosphere becomes, and thus the molecules are more diffused and there is less pressure because intermolecular space is greater. At the height of Mount Everest, the air pressure is about 2/3 less than what it is at the sea level. The air pressure is measured most accurately with the help of a mercurial barometer. For checking the accuracy of other types of barometers, the mercurial barometer is considered as a standard. In 1643, Evangelista Torricelli, a student of Galileo, made an experiment that formed the basis for the development of mercurial barometer, an instrument which measures atmospheric pressure accurately. He took a 3 feet long glass tube filled with mercury. He kept the top of the tube closed and inverted it into an open vessel filled with mercury. He opened the top of the tube only when it was beneath the level of mercury in the vessel. To his surprise, he saw that mercury in the tube fell until it was about a height of about 30 inches above the level of mercury in the pan, leaving a vacuum at the closed end of the tube. What happened was that the pressure exerted by the atmosphere on the open pan filled with mercury was equal to that of mercury in the tube. The rise and fall of the atmospheric pressure is indicated by a corresponding rise and fall of mercury column in the tube. The standard sea level pressure is given as 1013.25 millibars at a temperature of 15 degrees Celsius at a latitude of 45 degrees. This pressure is equivalent to 29.92 inches or 760 millimeters. The millibar is a force equivalent to 1000 dynes per centimeter, and a dyne is a unit force approximately equal to the weight of the milligram. Besides mercurial barometer, Fortin's barometer, there are other types of pressure recording instruments such as aneroid barometer, altimeter, or the altitude barometer, barograph, and automatic recording aneroid barometer, microbarograph, and microbarovariograph. This last pressure recording instrument is an extremely sensitive atmospheric pressure recorder. It records very small changes in the atmospheric pressure, changes of the magnitude of hundreds to thousands of the millibar. This instrument is so sensitive that it is capable of detecting even the minute pressure fluctuations produced by the passage of waves through air. Pressure fluctuations associated with the passage of severe atmospheric disturbance or even a large nuclear explosion in the atmosphere are easily detected by this sensitive pressure recording device. The air pressure recorded at different weather stations shows a marked variation, a fact that is of great significance in the analysis of weather conditions. As noted earlier, the standard sea level pressure is 1013.25 millibars, but the pressure changes from day to day and from time to time is never static. If we consider the sea level pressure observed over the entire Earth, it will be seen that it varies from about 982 millibar to 1033 millibar. The highest sea level pressure ever recorded was at Irkutsk in Siberia on 14th January 1893, where the observed pressure was 1075.2 millibars. The lowest sea level pressure ever recorded was observed in the eye of a very destructive typhoon that visited Mariana Islands. The pressure was abnormally low, 877 millibar there. All the weather changes are closely related to pressure variations. It is customary to believe that high values of air pressure produce clear and stable weather, while low atmospheric pressure brings in bad weather. However, it would be more logical to generalize that a continually rising air pressure is an indication of fine and settled weather, and a steady falling tendency in the barometer foretells the advent of unsettled and cloudy weather. In other words, despite the fact that air pressure is closely tied to various weather phenomena, it is due that the weather at a particular station is largely controlled more by the pressure in adjoining areas rather than the actual pressure recorded over there. The decrease of pressure between 2 points along a line is perpendicular to the isobars divided by the distance between the points is called the pressure gradient. In other words, pressure gradient is the rate of change of pressure per unit horizontal distance. It usually means a change in the direction perpendicular to the isobars. In fact, that is the direction in which the change is most rapid. The rate and direction of the change in air pressure are also known as barometric slope. It is expressed in millibars per 100 kilometers or per degree of the latitude. A decrease of 34 millibar in horizontal distance of 24 kilometers is considered to be a unit of pressure gradient. Thus, a decrease of 3.4 millibars in 48 kilometers or a fall of 10 millibar in 160 kilometers signifies a steep pressure gradient. Isobars are drawn closely on a weather map represent a steep pressure gradient, while isobars drawn farther apart indicate a weak pressure gradient. If we look at a daily weather chart, we will find a number of isobars drawn on it. On a closer scrutiny, we see that the isobars display characteristic shapes which indicate different types of pressure systems. These vary greatly in both size and duration. The semi-permanent high and low pressure cells do not make their appearance on the daily weather maps, but they appear on monthly, seasonal and annual pressure charts of the Earth. They are, of course, large-scale phenomena. However, there are various smaller, short-lived migratory pressure systems closely identified with daily weather changes that are seen on the daily weather maps. When the isobars are circular or elliptical in shape and the pressure is lowest at the center, such pressure system is called low or depression or cyclone. A line of low pressure is called a trough. Because of the lowest pressure at the center, the winds from outside blow and converge towards it. Thus, a cyclone is a closed system of isobars whose center serves as a focus for convergent circulation. Since under the pressure system, the pressure gradient is directed towards the center, winds blow spirally towards the central low pressure region. The Coriolis force that is produced by the rotation of the Earth causes the winds to cross the isobars at an acute angle. According to the Ferrel's law, the winds in the northern hemisphere are deflected to their right so that the direction of the flow is counterclockwise in this hemisphere, that is the northern hemisphere. On the contrary, the direction of the flow in a cyclonic wind spiral in the southern hemisphere is clockwise. For in the southern hemisphere, the winds deflect to their left. In a trough of low pressure, the isobars are V-shaped. In the northern hemisphere, the wider part of the V-shaped depression is always directed towards the north and the major axis extends from northeast to southwest. The low pressure systems are either semi-permanent or mobile. These pressure systems are characterized by high pressure centers or lines surrounded by lower pressures. Centers of high pressure are called highs or anticyclones. They being the highest pressure at the center, the pressure gradient is directed from center towards the outward margin. Therefore, in a high, the winds blowing spirally towards the outer margin. In an anticyclone, the direction of the flow is clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. Since in this pressure system, the direction of the wind movement is just the reverse of the cyclonic circulation, it is called anticyclone. When the isobars are elliptical rather than circular, the system is called a ridge or a wedge of high pressure. Like cyclones, the anticyclones also differ from one another in respect of their size, shape and other characteristics. However, the anticyclones are never so intense as the cyclones, but they are generally larger in size than the cyclones. The isobars are usually more symmetrical and are almost circular. The vertical structure of a cyclone or an anticyclone mainly depends on the temperature distribution within it. On the basis of the horizontal distribution of the temperature within the system, cyclones or anticyclones are classified in the following categories, which have been diagrammatically shown. Firstly, cold core cyclone, secondly warm core cyclone, cold core anticyclone, thirdly warm core anticyclone. The pressure and temperature distribution of the surface within these systems helps the weather scientists tell as to what may be the conditions aloft. It also proves to be an invaluable aid to the meteorologists in weather forecasting. Cold core cyclone. In this type of cyclone, the temperature is lowest at the center and increases towards the outer margin. Because of the contraction of the air column at the center and its expansion on the outer side of the low, the air pressure registers rapid changes upward. Thus, with increasing elevation, the barometric slope becomes steeper. If such lows are produced near the Earth's surface, they will increase in intensity aloft. If these lows form at some distance from the surface, then they grow weaker near the surface or they disintegrate. Ordinarily, the cold core cyclones form in the upper air. The semi-permanent Icelandic or Aleutian lows are typically examples of the cold core cyclones. Warm core cyclones. In these low pressure systems, the temperature is highest at the center and decreases towards the outer margin. In this pressure system, the air expands more over the warm central region than over the cool edges. Thus, the isobars spacing becomes wider and wider aloft until the load disappears. The vertical pressure gradient at the center is therefore low. In a warm core cyclone, the rate of decrease in the air pressure varies with altitude. At a certain height from the Earth's surface, the horizontal pressure gradient vanishes so that the isobars become horizontal and the low itself becomes non-existent. At higher levels, the low turns into a high. Such lows generally originate at or near the surface. The lows lying over the desert regions of eastern California or Arizona are the best examples of warm core cyclones. This variety of cyclone has a relatively larger rate of movement than the cold core cyclones. Cold core anticyclone. The cold core highs, as they are called, have low temperatures at their centers. They are generally shallow and are capped by the lows. At sea level, a cold core high weakens with elevation and may change into a high level low. Thus, a low forms over a high. The isobar spacing above the central core is less than that towards the outer edge. If the highs with a cold core form in the upper air, they intensify downward. The cold core anticyclones develop over the Arctic and Antarctic regions in the winter. On occasions, the cold core highs move into the warmer regions in low latitudes where they turn into deep warm core anticyclones by a process which is known in meteorology as dynamic anticyclogenesis. Warm core anticyclone. The highest temperatures in this type of circulation is observed at the center. The temperature gradually decreases from the center outward. Vertical spacing of the isobars at the center is relatively greater. At higher elevations, the isobars bulge out upward so that the slope of isobaric surfaces becomes steeper. That is why a sea level high with a warm core intensifies with increasing elevation. On the other hand, an anticyclone aloft in a warm air column diminishes in intensity or disappears towards the ground. The anticyclones of the tropical regions generally have a warm core. In the southeastern states of the United States of America and southern California, such highs form during the summer. According to Byers, the stratosphere above the warm core highs is exceptionally cold and high so that there is high pressure. To summarize what we have learned in today's class, air pressure and the different types, low pressure and the high pressure systems we have understood. Then we learnt about the cyclonic pressure systems, the cyclones and the anticyclones. The cyclonic system moves in anti-clockwise direction in the northern hemisphere and clockwise direction in the southern hemisphere, and the anticyclones move in clockwise direction in the northern hemisphere and anti